Here we have a series -1 to n plus 1 over n, and from 1 to infinity, alternating harmonic series. Want to know when our series is convergent or divergent? Well, let's try. I to apply alternating series test here. To this test, we need to check a few conditions. First condition, check that we have alternating series. Then we need to check first condition, which will say that limit of n equals to 0 when n is approaching infinity. And then we need to check second step, we need to check that an is bigger than an plus 1, that is an are decreasing. Okay, so we need to check these conditions. So we definitely have alternating series because that's the way we have series is written, -1 to n plus 1 divided by n. So alternating series, yes. Okay, so in our case is 1 over n, and if we take limit of n, which is limit of 1 over n when n approaches infinity, so we went at 1 over infinity, so it's 0. So we get yes for first condition. Now an equals to 1 over n, then an equals to 1 over n, an plus 1 equals to 1 over n plus 1, and when we compare 1 over n and 1 over n plus 1, the bigger the denominator, the smaller the fraction. So all conditions are satisfied. So all conditions of AST are satisfied. Therefore, we can make conclusion of AST, and conclusion of AST is this corresponding alternating series is convergent. So -1 to n plus 1 divided by n, and from 1 to infinity, alternating harmonic series is convergent by AST. That's the first example. Let's try another. Cosine of pi n multiplied by n divided by 3n plus 1, and from 1 to infinity. And we still have the same question. We want to figure out whenever that given series is convergent or divergent. So firstly, I want to get an intuition to what is going on. So I'm going to write down a few terms. For n equals to 1, n equals 2, n equals 3, n equals to 4. I'm going to write down it explicitly. So I'm going to get when n equals to 1, cosine pi divided by 4. When n equals to 2, I'm going to 2 cosine of 2 pi divided by 7. N equals to 3 cosine of 3 pi divided by 10. N equals to 4. I'm going to get 4 cosine of 4 pi divided by 13 plus and so on. Then I recall that cosine of pi is -1, cosine of 2 pi is 1. So our series is going to look like explicitly -1/4 plus 2 over 7. Cosine of 3 pi is -1, -3 over 10, plus 4 over 13, and so on. So from here, we conclude that the given series is alternating. If you like, we can rewrite it. We could rewrite it as n from 1 to infinity. So instead of saying cosine of pi n, we can write down -1 to n and divided by 3n plus 1. Anyhow, as soon as we realize that we have alternating series, what we want to do is we want to do alternating series test. Step 0. Do we have alternating series? Yes, we certainly have alternating series. Step 1. What is limit of n when n is approaching infinity? So we're going to get limit as n approaching infinity, and our n is n divided by 3n plus 1. So we're going to get, using the rule of thumb or using a L'Hopital rule, we should be able to get 1/3, and that is not equal to 0. So our conclusion, but the series, it is alternated, but we cannot apply AST to it. But because limit of a term is not equal to 0, by the comment which we did after our test, we conclude that this alternating series is divergent by dt. So we conclude that the given alternating series n cosine pi n divided by 3n plus 1 n from 1 to infinity is divergent by divergence test. Next theorem is continuation of AST. So that is alternating series test, error estimate. So what we do is we suppose that we start with the series -1 to n plus 1, an, n from 1 to infinity, and we assume that we are under condition of AST. So we assume that this series satisfies the conditions of alternating series test. Okay? Because series satisfy conditions of AST, it is convergent. So what we want to do is what do we do now is we have a convergent series, we want to approximate it. So we take the Kth partial sum and we say, well, that Kth partial sum is approximately to our infinite series. And we claim if the error, magnitude of error, EK, is going to be less than the next missing term, and it's going to be less than AK plus 1. And that's where alternating series test error estimate. So the idea of the theorem is the following. So if you have infinite alternating series, we can write it down like A1 minus A2 plus and so on, plus -1 to K plus 1 AK plus -1 over K plus 2. So what you notice here is that is SK, and that is our error. And if you look at our error, it's -1 to K plus 2 AK plus 1 plus -1 to K plus 3 AK plus 2 plus and so on. So what you notice is, like we did before, then it's going to be less. Then you will start combining by pairs here, and you're going to get that's going to be less than AK plus 1. So it's an idea. If you like, write it down explicitly a couple of times and you'll get a feeling for it. Okay, so let's try example on that. We already saw that alternating harmonic series is convergent. We already proved that. by AST. So the question is, how many terms would we have to add so that error, which is k, will be less than 0.001. So that error, magnitude of error, will be less than 0.001. Okay. So using AST error estimate test, we know that the error is going to be less than AK plus 1, and we wish it to be less than 0.001. So we're going to concentrate on second inequality. AK plus 1 is because we are working with alternating harmonic is 1 over k plus 1. It's going to be less than 0.001. Multiplying both sides by k plus 1, you're going to get 1 less than 0.001 times k plus 1. So k plus 1 is going to be bigger than 1 divided by 0.001. So k plus 1 will be bigger than 1 divided by 0.001 is 1000. So k is supposed to be bigger than 1000 minus 1. So choose first integer which is satisfied. So we need to add 1000 terms so that the error will be less than 0.001. So a lot. Definition. We say that we see this infinite series is absolutely convergent if which consists of absolute values of n is convergent. If this is convergent but not absolutely convergent, we say it is conditionally convergent. Couple of examples. Look at the series -1 to n plus 1 over n from 1 to infinity. By AST, it is convergent. If we look at the absolute values, series of its absolute values, we're going to get harmonic series, and that is going to be divergent. Therefore, by combining these two pieces of information together, we conclude that n from 1 to infinity, -1 to n plus 1 divided by n, alternating harmonic series is conditionally convergent. So, absolute convergence implies convergence. Let me restate that maybe in more formal way. If the series of n from 1 to infinity is absolutely convergent, then the series is convergent. If we looked for series -1 to n divided by n squared, n from 1 to infinity, and we wonder whenever that series is divergent to convergent. Let's try. Of course, we can do AST. That's a possibility. But it's so much quicker, look at the series which will consist of absolute values of the terms. So 1 over n squared. We immediately know that it's p equals to 2, p series convergent. So we turn around, we conclude that the original series and from 1 to infinity is convergent. Because it is absolutely convergent, therefore it is convergent.